Okay, let's go over a few more things. Okay, so I can't remember if I used 31 flavors or 32 flavors in the video that I made before. I guess it doesn't really matter. Okay, let's say they have 32 flavors. So 32C3 would be if you're interested in, say, a bowl of ice cream, because you're only interested in the selection of the flavors. Okay, so what's that going to look like? It's going to be 32 factorial over, and then I have to subtract those two. Okay, so that is going to be 29, and then 3 factorial is going to be the rest of that formula. Okay, obviously I could simplify that and so forth, and of course I could evaluate that on my calculator, and it's going to be big. Okay, if I want to find 32p3, that one's just going to be 32 factorial over 29 factorial. Okay. Obviously, hopefully you see that this set is 6 times bigger than this set simply because you don't have that extra division involved for that set. Okay, so this is 6 times as big, this one, as that first one. Okay, so what I'd like to do now is to go over some problems that aren't really exactly combination problems, and they aren't exactly permutation problems. So like, let's look at one of those examples. Okay, so let's say for instance you have the word Mexico and you have the word Canada. Okay, so sometimes, let's say you're a puzzle designer, you might be interested in scrambling these words up, and then people have to kind of guess and figure out what they are. Now, obviously, you could probably figure those out pretty easily, but obviously for one of these, there's more ways to scramble it than the other one. So if this, I want to consider all the scrambles of that, and I want to say I include the original one in there just because it's easier. There'd be 6 factorial ways to scramble all those letters. Basically, it's again just kind of going back to the original definition. What does 6 factorial mean? It means the ways to arrange 6 things, okay, into say 6 slots or that sort of thing. Okay, so for this one, hopefully you realize that like the way they're all written with capital A's, like, I can make an arrangement, and then while you're gone, I could like switch 2 of the A's, and then ideally you wouldn't notice that I switched them, or I could switch all 3 of them around in some way, and then it would still appear the same to you. So several arrangements of those things are going to really appear the same. So how do I account for that? It's going to be 6 factorial over 3 factorial. And the 3 factorial really counts for, there's 3 factorial ways to arrange 3 individual things, like 3 letter A's. I could call them like, A1, A2, A3, and then consider all the ways to arrange those. Well, there's 3 factorial ways to arrange those, but I'm interested in dividing those out because I really don't want to consider those additional rearrangements of the A's within an arrangement, any additional arrangement. So that's going to account for that. Okay, so let's do a sort of a fun problem. Let's say I want to rearrange the letters in Cincinnati, like a word scramble. Okay, first of all, I would, to consider all the ways to rearrange this, I would count all the letters here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 things. So if there were 10 unique letters, then there'd be 10 factorial ways to arrange those letters. Of course, they're not all unique. So what I have to do now is find the duplicate letters, okay? So there's, like, for the ends, right, there's 3 factorial ways I could rearrange the ends. I want to divide those out. And then for the C's, right, there's 2 factorial, they're the same for this one, ways I could rearrange the C's, right? And then the I's, there's 1, 2, 3 I's. So I would want to consider, again, divide out those rearrangements of the I's. Okay, so there's actually only this many ways to arrange the letters in Cincinnati. Obviously, you could work through that yourself and kind of see what that answer is. Okay, all right, so let's do another one like that one. M-I-S-S-I-S-S-I-P-P-I. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 factorial. Okay, and then let's count the S's. So 1, 2, 3, 4 S's. So 4 factorial. And then I's. 1, 2, 3, 4 I's. Got to divide those out. Okay, so I've counted for all of those, and then the only thing now that's out is the P's, so there's going to be 2 factorial ways that I can consider rearranging those P's. Let me write those underneath. P, and then I, and then S's. Okay, and of course, once I have those, there's only M. Obviously, I can write 1 factorial for the M. That's not really going to make a difference. Hopefully, you get the principle on those. Okay, all right, so let's do another problem, which is kind of related to that. Let's say that there's a core workday. Oh, what a thought, a core workday, and we all love that. Okay, so on the core workday, let's say there's 10 students, okay, and we'll say that they have different roles in the core workday. We have to assign different jobs. Okay, so let's say there's weeding, okay, to do, and then let's say there's dusting to do, and then let's say there's also, let's say it's the end of the year, so they have to like sort through books or whatever and put them away. So there's sorting to do. So there's weeding, there's dusting, and there's sorting. Okay, and let's say there's a lot of weeds because, you know, it's been raining a lot and stuff like that. So let's say we need 4 people, to do weeding, and then dusting, let's say we need 3 people for dusting, okay, and then sorting, let's say we need 3 people for sorting books out at the end of the year. Okay, all right, so let's say anybody can do any of those tasks, which is kind of an assumption you'll have to make in a later problem that I give you. Okay, so it sounds kind of weird, but believe it or not, the ways of assigning jobs in this situation is actually analogous to making letter rearrangements of this word, okay? So what you can think of doing is, you know, you could have either these letters in a box and you pull them out and give one to each person, or you slap a badge on their chest and just say, you're a weed person, you're this, you're this. So if you think about it, though, it's rearranging these things is really the same as assigning jobs to those 10 students. So let's think how we do that one. So there's 10 factorial if they each had different jobs, right? But since they're going to be sort of slotted into categories, okay, so I'm going to divide by 4 factorial for all the people that do the weeding, okay, and 3 factorial for all the people that do the dusting, and then, oh, no, sorry, S, 3 factorial for the people that do the sorting. Okay, so obviously you could run through a calculation like that on your calculator. But this is an example of a problem that's not exactly a permutation problem or a combination problem. It's kind of like a mixed problem. On the other hand, it's like a lot of times you get problems like this where it's sort of a mixture of different problems kind of put together. And so I think if you have like a good overall understanding of like the combination problems, the permutation problems, even some of the mixed problems, you know, you'll just come away with like a really robust understanding of this. Okay, so let's look at one more problem. Let's say we have 10 students, okay, and what we're interested in doing, okay, is having a president and then a vice president, and then we're interested in like a 3-person committee. Okay, so this again, it's really a combination problem for this one. Okay, all right, so if you think about it, for the 10 students, okay, there's really like 10 ways I could assign president, or yeah, assign it or vote it or whatever, and 9 ways then I could do vice president. Okay, now at this point there's only 8 students left, so I could assign the next role in 8 ways, the next role in 7 ways, the next role in 6 ways. Now the problem is those are interchangeable. So what I'm going to call those are indistinguishable, okay? So if I chose like Alex, Veronica, and Alyssa for this role, it's the same as Alyssa, Veronica, Alex, etc. I want to divide out those rearrangements, okay? So what it would look like is 10 times 9 times 8 I'm sorry, yeah, times 7 times 6. And then, like, it's going to be divided by 3 factorial to account for those rearrangements. Okay, so you could think of it this way. Another way you could add to it, so that would be the answer. But if you wanted to think of, like, instead, what you could do, it sounds kind of weird, but you could go back to the original problem for a minute. Okay, and if we wanted to account for all 10 people, okay, I could call the last 5 people having no roles whatsoever, okay? So if they have no roles whatsoever, they're kind of equal in that sense. So one way I could sort of add to the problem, it sounds kind of weird, I could do like 5 times 4 times 3 times 2 times 1 sort of here, and then divide by 5 factorial. So of course this is going to be 1, so you don't really have to show it in the problem, but again, what it's kind of weird, what's kind of, and what I want to draw the connection to is it's sort of analogous to, I pick a president, I'll use V for vice president, V, and then I have, let's say, 3 people that are on the committee, okay, and then I have 5 people with no role whatsoever. Okay, so again, what I could do is treat it just like a letter problem, okay? So how many ways are there to like manipulate all those letters? It's going to be 10 factorial, okay? And then I'm going to have to divide by 3 factorial to account for the people in the committee rearranging out those rearrangements. And all of the people that have no role, well, they're indistinguishable too. So that any rearrangement of those guys, it's just going to, you know, we don't want to really account for that. So that's going to be 5 factorial. Okay, so if I look at that really carefully, this does compare to this. So I want to say, if you're comfortable with those letter rearrangement problems, often for other problems, you can, it sounds kind of silly, but you can map those problems onto a letter rearrangement problem, and then you can solve it that way, if that makes sense. Okay, good luck with the assignment.